Okay, so our next speaker is Professor Srinivasan Parthasarathy. Professor Srinivasan is the director of the Data Mining Research Laboratory, which is a part of the High-End Systems Group and affiliated with the Laboratory for Artificial Intelligence Research at Ohio State University. He's also the co-director Data Analytics Program at Ohio State University, and he's broadly interested in the areas of high-performance data analytics, graph analytics, network science, machine learning, and database system.
Thank you, everyone. Thank you, organizers, for the invitation to speak here, and thank you, Sriram, for setting the stage perfectly for the talk I'm about to give, because some of the things that Sriram was just talking about are front and center in the context of what we are looking at here. So what we're going to do in this talk is do a deep dive in a particular application of great interest worldwide, especially for humanitarian agencies like the UN agencies, as well as FEMA, Red Cross, and so on and so forth. So what I'm going to sort of try to organize this talk in is we're going to do, I'm going to try to give some motivating examples about why this is an important area to think about, especially from a social good perspective. And then subsequently going to take a little deeper dive into some of the technical details. Given the length of the talk, I'm going to try to limit some of that and then present some of the results we have. One of the things is that this is an example of, what I'm going to discuss today is an example of this notion of, human machine teaming working in practice. While it does not have all the functionalities of a fully integrated autonomic teammate, it starts to head in that direction, as Sriram was talking about. When towards the end he was talking about assisted learning and advice and things like that. So some of those elements will show up in this talk. Now, to give you some background, flooding, especially those induced by cyclones and hurricanes, happen quite dramatically and quite suddenly. In fact, as this image here is showing, you have individuals who are completely submerged in the middle of a street. And we saw this, and in fact, for many of you who are back in Chennai, we saw this repeat itself in the month of December of 2015 and 2016, where we had a series of depressions. Then most recently, there was this cyclone that went through good parts of West Bengal and Orissa that again had a similar scenario. So this is something that is a worldwide phenomenon. In the US, as well as many other parts of the world. Brazil had one of the largest floods in Sao Paulo a couple of years ago. Similarly, these disasters are just simply increasing as the years go by. Why are we focusing on floods? Much of what we can talk about here, or what we are doing here, could potentially be applied to other disasters, but floods are the single largest natural disaster that impacts the world today. In fact, if you add up the next three, disasters of importance, floods still overwhelm them in terms of both the cost to human life, as well as economic cost, as well as putting people out of their homes and things like that. Now, the specific challenge we are going to talk about in this talk today is flood mapping, and that is defined by Martinez and others in the remote sensing community as the process of distinguishing waterlogged or flooded areas from non-flooded areas, especially immediately during and immediately after a disaster like a cyclone or a flash flood and things like that. Now, this kind of flood mapping is directly usable. It's got a direct practical application in the sense that it guides first response resources, essentially immediately after a disaster situation, in terms of assessing both flood risk as well as assessing, what are the infrastructure components that make a particular region, an urban or a rural region, that is very important for that region, and what needs to be fixed and how to prioritize all these efforts. And so this is something that these kinds of flood maps are particularly useful for. So the challenges, especially with respect to some of the machine learning models, especially those that come out of the computer vision side of things, is that these water areas are, especially when the flooding is unpredictable in the direction of wind speed, and there are all these other factors. They come in arbitrary sizes and arbitrary shapes. Some of the ideas from the literature work up to a point, but they're simply not sufficient. And we'll talk about some of those in a few slides. Now, one of the things we'd like to do is ally with humans, and humans, of course, they carry with them a lot of ability, but they often get overwhelmed with huge amounts of data, and so they also have limited time. And for instance, in this kind of work, identifying these waterlogged areas, you need a level of expertise typically in order to do a good job. And so one of the things we'd like to be able to do here is democratize the process, so that we have a lot of, every time a crisis hits anywhere in the world, there are a bunch of dedicated volunteers who are more than willing to help, but they may not have the technical expertise of a remote sensing flood expert. And so how can we accommodate some of their abilities and make this process a little more democratized? And so that's one of the things we're going to examine here. The other aspect of this, as I mentioned, is that the amount of data easily overwhelms human cognitive capabilities. And so one needs to, bring this down so that there isn't that much cognitive overload, so that the human can actually assist in this process. And so these are some of the questions we'd like to be able to answer in this talk. So what I have here is a typical image from Sentinel-1, which is a satellite that, a geospatial satellite that a lot of agencies across the world use for these kinds of problems. And what I'm showing you is an overlay of a picture of a snapshot taken above the landscape in and around Chennai and Tamil Nadu during one of the disasters that took place in 2015 and 2016. So this is just an example of the kind of image that we have to label. And as you can see, you have these varying sizes of darker spots separated by lighter spots, and one has sinuous rivers that one has to accommodate in this kind of flood mapping, and looking at regions next to rivers and things like that. So this is quite a challenging task. So an overview of the idea of what we're going to do is we start with something like the satellite image from Sentinel-1, and then what we want to do first is, again, to reduce the cognitive overload on the human assistant, we want to group some of these things together using a clustering function. I'll talk about how we do this. We refer to these as patches. We then want to take these patches and selectively give some of them to the humans for supervision, to get labels on these images. And once we have that, what we'd like to be able to do is use that information, that semi-supervised information or partially supervised information from the human assistant, to try to classify the rest. And then we produce a map that the human can look at. And then what I'm not showing in this slide is there's a loop back. There's a form of active learning going on. Again, Sriram referred to that at the end of his talk, where the human can update the map that is produced, and we can continuously learn and improve the performance of this algorithm. So this is just at a very high level what the approach is looking at. So how do we go about? Let's go through each of these steps in turn. So how do we generate these patches? And again, in this particular cartoon image, I'm showing very large patches. This is not how we do it, obviously. So I'll get into the detail about specifics in the next few slides. So again, why are we doing this? These are easier to label, and we want to reduce the overload on the human side of things. So again, if you want a human allied system, you have to understand both the limitations of the human as well as the machine agent. I mean, machine agents are very good at processing large amounts of data, but they may not have a complete understanding of the behavior of the natural system, which humans may be able to provide. And similarly, on this side, humans cannot handle too much data. They're easily, the cognitive overload becomes too hard. So you have to come up with a system that marries the strengths of both while mitigating the weaknesses of both the human as well as the allied agent. So again, we want to do this patching because we want to make things easier on the human. And there's also an efficiency argument to be made in this kind of approach. So we are using a standard approach from the image processing literature. And it essentially follows a graph-based clustering approach to generate patches. So you have this very large multi-resolution image, and each pixel in the image can be treated as a node. So again, Sriram referred to graph algorithm. So this is an example of a graph algorithm that we're using in this particular context. For two nodes, I and j, the weight of the edge is defined using this Gaussian difference weighting function. Again, this is a fairly standard. If you look at this particular weighting function, if the two pixels are close enough, and that's what's determined by d max in the equation here, then there is a weight attached to them. If the two pixels are too far apart, they do not really have an impact on each other. So the weight is 0. And again, this is just a standard function that we follow precisely what Core and others have done. So distance ij represents the distance between node I and j in terms of pixels. And the feature difference looks at the different, so each pixel comes with it a set of features. I mean, it could be, features that are taken from the SAR image, as well as, pixel intensity, the color, and so on and so forth. And these are, one can use different distance functions here. We just use a standard one that was suggested by Core and others in their paper in 2005. And then there are some hyperparameters that have to do with, the kernel width and so on and so forth that you need to look at. Now, once you have this graph, we leverage a standard stochastic flow clustering algorithm called MLR-MCL to essentially cluster this graph in order to generate the patches. And so what you're looking at is an image like this. What I'm showing you on the left is an example of a SAR image from the Houston area. And as you can see, what we're trying to do, if I blow up one small area of that particular image that we're looking at, you can see that the patches have done a fairly good job of trying to isolate the sinuous, riverbed that is going around like this. The darker patches and the lighter colored elements are all separated out. And so this algorithm does a pretty good job, does not require you to specify the number of clusters. It's a fairly natural algorithm, the stochastic flow algorithm. So it works quite well in this particular setting. So that's step one, which is generating the patches. In the second step, what we looked at in this context is we need to get labels from experts, ideally from remote sensing experts. But again, there are few of them, relatively speaking. So eventually, we want to be able to take this to the crowd. And so that was sort of the background argument for the ideas here. So our desiderata is that we want to be fast, scalable, and accurate, and we want to try, ideally, to get information about patches that the system is generally most uncertain about. And that's where some of the active learning aspect comes in. I'm not going to go into the details on that, but that's coming up with an estimation of which areas you're most uncertain about is part of the challenge. And you get to this through an iterative process. So initially, when you know nothing about it, system starts with 0. All of them are equally uncertain. But over time, you can improve on this. And so that's part of what we're doing in this effort. So once we generate these patches, the expert is asked to label a few of them. And so that's what you're seeing over here with the 1s and 0s. They're trying to label some of them as waterlogged areas and other parts of it as, more less waterlogged or land areas and things like that. Now, we tried a few different algorithms. We finally settled on a fairly simple idea, KNN semi-supervised classifier, which uses some of the features from the image like lat long, elevation, different types of satellite channel polarity features, and so on and so forth. But we found that the KNN-based approach seemed to do as well as slightly more complicated ones, so we stuck to the simplest approach that worked for us. And then, of course, if, as I mentioned previously, if the resulting map is not up to the mark, this can continuously be improved over as the system interacts with the human ally. So what I'm going to do now is I'm going to so that gives you the patches classification, and of course once you have the patches classification, that sort of gives you, essentially you can overlay that on the region on the satellite image, and you can get a flood map, so to speak. So once you have the classifier working, you can apply that classifier on all the patches in your satellite image, and you essentially get a flood map of the region you're trying to model. And this gives information to first response folks in the particular region. And so this is where they can use this for prioritization efforts and so on and so forth. Now, as you can imagine, this is an idea that, or this is something that the geospatial and remote sensing community has been looking at for many, many years. So they have algorithms that they've been using. And the other challenge with this particular domain is getting very good curated gold standard data sets. So what I'm going to show you are results from two particular areas. And later on I'll talk about a third area. But particularly the two areas that we're going to look at are the Chennai floods in 2015 and floods in Houston in 2016. And later on I'll talk about some floods that happened in the Carolinas in 2018 and 2019, very briefly. But one thing to point about the two data sets: the first data set is not curated. It's sort of, you just look at it, and we are going to visually and qualify and look at this and see how it does. The second data set is a painstakingly curated data set that has taken experts in the range of somewhere in the range of 6 man-months to specifically curate every single pixel in these images, as whether it's waterlogged or not. And so this is a gold standard data set, the Houston data set. And so we're going to use this for some of the quantitative experiments. And this is something that our group had done as part of a large hazard seas project funded by the National Science Foundation. So again, as I said, there are many algorithms, both from computer vision as well as from the remote sensing community. And we're going to look at some of these, how these different algorithms perform on these data sets. So first, we're going to look at a data set from Chennai. This was in 2015. This was right around the time of the second depression. The third depression hit the city the worst. But by around the time of the second depression itself, things were pretty bad. I actually happened to be in town at that time, so my trip to the airport was quite interesting, through waterlogged roads and using an SUV to get to the airport. One of the last flights to take off at that particular time. So again, what the algorithm I described, we call it CHUG-FM, so human guided flood mapping. This is an algorithm. The watershed algorithm is an algorithm that is used by the remote sensing community a lot. Normalized cuts is the venerable seminal work of Malik and Shi, and there, of course, there are other algorithms, but you can see that of all of them, the most natural one is the one that we are looking at. And again, this is a qualitative study for the Chennai data set. We do not have curated gold standard ground truth, but you can see from the images that there's a very natural boundaries that this particular approach is able to achieve. Now, if you look at a comparison of, you want to look at human effort, you want to look at the time it takes for the algorithm to run. Again, if you look at the running time comparison, you can see that, some of the two algorithms that are from the remote sensing community, they're fairly fast. CHUG-FM is also fairly fast. This does not include the time the human takes to do some of the labels. But for this entire image, for example, the human effort essentially required labeling 2 patches of this entire image. So the human effort was not that significant. And then some of the other methods are much more expensive in terms of time. So this just gives you an idea of that aspect. We did the same kind of analysis on the gold standard data set where we had exact information. So here I'm able to give you more quantitative ideas of how well things are, how well things can be done in this particular space. So again, when you compare against some of the more recent machine learning algorithms like Planetoid, which is a partially labeled attributed network algorithm for semi-supervised learning, SVMs, which is again slightly older but still quite effective. Again, on this gold standard data set, again, you see that the human guided approach does very well on the metrics of accuracy and F1 score. And this is just standard harmonic mean of precision and recall, the F1 scores. So moving on, the sort of next thing that we started thinking about is that you don't always have enough time from experts when a crisis is evolving. And so can we take some of these ideas and move it to the crowd? That was sort of the question that we were focusing on for the next part of what we were looking at. And so but what we ended up doing was setting up a crowdsourcing platform that looked something like this, where you show patches to individuals using this context. And again, for experts, we didn't need to do this, but for crowdsourced volunteers, we wanted to make sure that we could show them the context of the pixel in terms of the larger image so that they have a sense for where they are looking at. And again, we provided the same interface for the experts. The experts did not really need that information, but this we found was particularly useful for the crowdsource volunteer group that we were focusing this on. The other thing we needed to, so the interface looks something like this, where the crowdsource volunteer would go in, get the context information, and then pick one of these, whether there's waterlogging, whether it's not waterlogged, regular land, or whether they are uncertain about what they're looking at. So each crowdsource volunteer had to do this for several markers. And then once they completed their task, what is shown is what the result of their effort looked like. Now, you can see that from this image, if you look at this particular image compared to some of the things we showed with the expert, it's not as good as an expert. But what we're hoping for is that, if a crowd of these people do this, as long as the errors are not correlated across them, we can perhaps achieve at least as good as an expert or close to an expert. And so one of the other things we had to do as part of this effort is that since experts can select which patches to label, whereas in this case, we did the crisis volunteers did not have enough domain expertise to figure out, which patches that they felt that they should really address. We had to figure out a way to stratify the sample and provide, so that we had a good coverage of both uncertain regions as well as clearly, land or water regions, so that we can do a better job. So there was some underpinning effort in terms of setting up the crowdsourcing environment in terms of, which samples that these folks had to label. And once we had those labels from these crowdsourced folks, we combine them. We have a weighting scheme. It draws inspiration from some nice efforts in ensemble learning. For this particular study, we looked at 53 college-educated participants. Several of them did have a background in geography, but not all of them. I mean, it was something like maybe 10 or roughly about 15 to 20% of these individuals had a background in geography, but the rest were just college-educated folks. And they were asked to work on the Houston dataset and 2 of the Matthew datasets. And so what I'm going to show you here is how these results compare. So this is more of a qualitative analysis. So this on the left is the original SAR image. On the right is the of what we are getting with human guided expertise from experts, CHUG-FM. And on the right and on the extreme right, we're getting what the results look like from the crowdsourced CHUG-FM. And as you can see, the results are quite comparable and quite consistent with that of an expert. So drilling down a little more on this particular gold standard Houston data set. So if you take CHUG-FM by a single expert, the accuracy is highest when compared to the CHUG-FM by a single member of the crowd. Even when you look at average, or if you account for, deviation effects, the best of the individuals was not approaching that of an expert. However, when you combine them through weighted voting, through this crowdsourced environment, they did do better than a single expert could. And so this is a way in which you can democratize this process through this, human AI alliance. Now, again, in terms of time, the average time that a crowd member or a crowdsourced volunteer spent on this particular task was about 6 minutes across 3 data sets from 3 different disasters. And so again, we did a user study that looked at, rating the interface, rating the clarity of the instructions. Not particularly relevant to this talk, but I include those results and that information here as well. But again, if you look at the amount of time spent by each volunteer, and again, remember that this can happen in parallel. You can have multiple volunteers going through the system at the same time. It supports concurrency up to 1,000 volunteers at the same time, the system does. So this system is something that has been deployed. So humanitarian agencies are using some elements of this system for some of their work for flood mapping. As I mentioned up front, this is a challenging problem for relief prioritization post-disaster. What we talked about very, very briefly here are 2 strategies. One that seeks the guidance from an expert. It produces high-quality, scalable mappings with minimal human guidance. As I said, in the context of the expert, we only looked at, for some of these images, we only needed to get information from 2 or 3 markers. Of course, these were 2 or 3 markers that that the expert felt the machine would find difficult. So the expert actually used some of their domain knowledge for this aspect. And it outperformed the state of the art in the remote sensing community, as well as some of the standard methods from the computer vision community. And the second part is how we can take this to the crowd. I mean, how we can democratize this process so that we can take advantage of the lively group of volunteers, passionate volunteers, I might add, who spend a lot of their time helping out people around the world with these kind of crisis response organizations. And I have a great deal of admiration for their passion and support for these kinds of efforts. And again, we can produce comparable mappings to that of an expert. Sometimes we can actually do better. And we have some results in a paper that we presented at the web conference a year or so ago. Now, I think I'm out of time, so I'm not going to talk about some ongoing work that we have. But one of the things we're looking at right now is how we can understand differences in land cover and differences in water logging over time. And so this is something that crisis volunteers, not crisis volunteers, this is something that humanitarian response agencies are particularly interested in because they want to assess flood risk. And this has downstream applications for insurance and other kinds of activities. And so, and it also has importance for constructing, from a civil standpoint, constructing methods or mechanisms to mitigate these kinds of damages in the future. In fact, as you can imagine, the Netherlands is a leader in this space. And so we're working with some agencies over there looking at some of these things. So at this point, I'm going to stop.